Sea ice looks like a lid. For decades, climate models often treated it that way too, a frozen barrier separating the polar ocean from the atmosphere and largely preventing gases from passing between them. But a new synthesis of more than 6,000 direct measurements shows that this picture is wrong in a surprisingly complicated way. Sea ice can release carbon dioxide in winter, absorb it again in summer, and continue exchanging gas even when temperatures are far below freezing. Yet after all of that seasonal activity is added together, its total effect on the polar carbon budget is much smaller than many scientists once suspected. The study, published in Nature Communications, assembled 6,298 chamber measurements collected between 2003 and 2021 during 14 Arctic and 8 Antarctic field campaigns. Of those, 4,719 measurements came from the Arctic and 1,579 from the Southern Ocean. It is the first basin-scale synthesis of direct air ice carbon dioxide exchange across both polar regions. The result transforms sea ice from a simple physical cover into something more like a seasonal membrane, one that opens, closes, stores, releases, and absorbs carbon depending on temperature, ice structure, snow, melt ponds, brine, and the time of year. When seawater freezes, pure ice crystals form first, while much of the dissolved salt becomes concentrated in pockets and channels of salty liquid called brine. Sea ice is therefore not one solid, impermeable block. It contains a microscopic network of liquid channels, air spaces, cracks, and bubbles. Carbon dioxide can be dissolved in the brine, trapped as gas, transferred from seawater below, or exchanged with the atmosphere above. Scientists have known since the 20th century that sea ice can be permeable, but the significance of this process for the carbon cycle remained uncertain because direct measurements were sparse and difficult to collect. Collecting those measurements is much harder than it sounds. Researchers often place a small sealed chamber directly on the ice surface and monitor how the carbon dioxide concentration inside changes over several minutes. If the concentration rises, the ice is releasing CO₂. If it falls, the surface is absorbing it. This method has been used across different kinds of sea ice, including first-year ice, multi-year ice, snow-covered surfaces, bare ice, and melt ponds. It provides a direct measurement of gas movement, but doing it in polar winter means working in darkness, extreme cold, moving ice, and dangerous weather. That difficulty is one reason winter observations remain much rarer than spring measurements. When the researchers combined the full data set, a strong seasonal rhythm appeared. In Arctic winter, from January through March, sea ice acts as a net source of carbon dioxide. The study estimates that Arctic ice releases roughly 6 teragrams of carbon during this period. A teragram is 1 million metric tons, so even though the flux through each square meter of ice is small, the enormous area of the Arctic makes the seasonal total measurable. At the same time, open water within the Arctic sea ice zone behaves very differently, absorbing approximately 19 teragrams of carbon during those winter months. Why would freezing ice release carbon dioxide? As seawater freezes, salts and dissolved substances are squeezed into increasingly concentrated brine. Carbon dioxide and other forms of inorganic carbon can become concentrated there as well. Young, thin ice is especially permeable, allowing this carbon-rich brine to remain connected with the atmosphere through channels and cracks. The new synthesis found that newly formed thin ice can release substantially more CO₂ than older, thicker ice. Mature ice becomes less permeable as its brine network changes, reducing the connection between the ocean, ice, and atmosphere. As temperatures rise, snow melts, the structure of the ice changes, and carbon dioxide uptake starts to increase. By June in the Arctic, the median measured flux becomes slightly negative, meaning the ice is absorbing carbon dioxide rather than emitting it. In summer, the pattern becomes clearer. Arctic sea ice acts consistently as a sink, drawing roughly 3 teragrams of carbon from the atmosphere during July through September. More than half of that summer uptake is associated with melt ponds. Those bright blue ponds that appear on Arctic sea ice are therefore doing more than changing how much sunlight the surface reflects. They also participate in gas exchange. The study found median carbon dioxide uptake over melt ponds stronger than over much of the surrounding summer ice. Their liquid surfaces and chemical conditions can create an efficient connection between the atmosphere and carbon stored within the ice-ocean system. By autumn, however, the direction changes again. Freezing resumes, fresh ice forms, brines become concentrated, and the system returns toward net carbon dioxide release. The Southern Ocean shows a broadly similar seasonal cycle, although the timing is reversed because the seasons are opposite. Antarctic sea ice releases carbon dioxide during winter, shifts toward uptake during spring and summer, then returns to release in autumn. The researchers estimate that winter sea ice in the Southern Ocean releases around 2 teragrams of carbon, while spring and summer uptake offset much of that emission. This seasonal reversal was one of the clearest patterns across both polar regions. At first, all of this sounds as though sea ice might play a major role in controlling atmospheric carbon dioxide. Earlier estimates even suggested that Antarctic sea ice could account for a very large fraction of the Southern Ocean's annual carbon uptake. But the new global compilation produced the opposite conclusion. After winter emissions and summer absorption are combined, the annual balance is small. Arctic sea ice is estimated to be a net source of about 4 teragrams of carbon per year, while Southern Ocean sea ice contributes about 2 teragrams per year. Those numbers need context. Open water in the Arctic sea ice zone absorbs approximately 100 teragrams of carbon per year, according to the study's comparison. In the Southern Ocean sea ice zone, open water absorbs roughly 38 to 60 teragrams annually depending on the estimate used. Sea ice, therefore, accounts for less than about 5% of the annual regional ocean carbon uptake. The seasonal exchange is real, but at basin scale the much stronger air-sea exchange through open water dominates the budget. The first old assumption was that sea ice simply blocks gas exchange. That is clearly false. The second emerging idea was that because sea ice does exchange carbon dioxide, it might represent a major hidden carbon sink. The new synthesis suggests that this is also unlikely. Sea ice is chemically active, but its winter emissions and summer uptake mostly cancel each other out. There is a useful analogy. Imagine a bank account with large deposits every summer and large withdrawals every winter. Watching only one season could make the account look extremely profitable or dangerously negative. But when the entire year is calculated, the balance barely changes. That is essentially what researchers found with polar sea ice. Short campaigns conducted during only spring or summer could produce a distorted picture of its annual role. A full seasonal view shows that the direction repeatedly reverses. This also explains why earlier estimates varied so widely. Polar fieldwork has always been biased toward the seasons that are easiest to access. The study notes that around 80% of Arctic measurements and 60% of Antarctic measurements in the database were collected during spring. Some months in the Southern Ocean have no chamber measurements at all. Researchers therefore had to extrapolate from nearby months when estimating the annual budget. The authors emphasize that substantial uncertainty remains, particularly in winter and autumn. A chamber placed over the ice blocks wind, reducing turbulence, and a process called wind pumping that may help gases move naturally through cracks and pores. That means chamber experiments largely capture diffusion and may underestimate some real-world gas exchange. Sea ice can also change rapidly over a single day. During spring, daytime warming can cause carbon dioxide uptake, while nighttime refreezing can reverse the direction and produce emissions. A researcher measuring for only 30 minutes may therefore observe only one phase of a much faster cycle. Even with those uncertainties, the study delivers a strong message for climate models. For large-scale carbon budget calculations, explicitly representing direct carbon dioxide exchange through sea ice may not dramatically change the global result because the net annual flux is so small compared with open ocean exchange. The authors actually conclude that treating sea ice CO₂ exchange as negligible may remain defensible for broad Earth system carbon budgets until better parameterizations become available. But that does not make the discovery unimportant. The mechanism may matter far more for other gases. Sea ice also exchanges substances such as dimethyl sulfide, volatile organic compounds, and halogens. Unlike carbon dioxide, these trace gases do not necessarily have an enormous open ocean reservoir dominating the signal. Even modest exchange through the ice could significantly alter atmospheric chemistry, cloud formation, or regional radiation. The authors specifically warn that a small role for CO₂ does not mean sea ice can be ignored for all atmospheric gases. Climate change adds another complication. Arctic multi-year ice is declining and increasingly being replaced by thinner first-year ice. According to the study, thin young ice is generally more permeable and can release more carbon dioxide during formation. At the same time, more summer open water replaces relatively weak air-ice fluxes with much stronger air-sea carbon exchange. The carbon cycle of a future Arctic with less old ice may therefore be controlled increasingly by open ocean rather than by the ice surface itself. That is why this research changes the picture of polar sea ice without turning it into a dramatic new climate feedback. The ice is not a sealed lid, it breathes. In winter, newly forming ice can release carbon dioxide through salty brine networks. In spring and summer, melting surfaces and ponds can pull some of that carbon back from the atmosphere. The direction changes with the season, the type of ice, and the state of the surface. Yet over a full year, most of those exchanges cancel one another. For decades, the frozen poles were simplified in carbon models as barriers between air and sea. More recent research replaced that picture with the idea of an active carbon pump. The largest synthesis yet now reveals something more subtle. Sea ice is active, porous, and chemically alive, but it is not a major missing carbon sink. Its real importance may lie in the rapid seasonal processes happening on small scales and in the other trace gases moving through the same hidden channels. A surface that looks solid from space is actually exchanging material with the atmosphere all year long. The surprising part is not that polar sea ice controls the carbon cycle, it is that it can breathe carbon in both directions while leaving only a remarkably small annual footprint.